Picture a really heavy industrial factory floor. Like you've got massive robotic arms welding steel, high voltage equipment firing off everywhere, and just this chaotic storm of electromagnetic interference in the air.
Oh, yeah. An absolute nightmare for any kind of sensitive electronics.
Right. Now imagine trying to maintain a perfectly stable, microsecond accurate data connection right in the middle of all that noise,
Hmm.
and doing it using nothing but a standard off-the-shelf smartphone.
Which sounds completely impossible.
It really does. You would assume the phone would just, melt down or constantly drop the signal. But we are looking at a fascinating stack of highly technical specification documents and white papers today. They detail something called the SS-138 Architectural Protocol.
Yeah, it's a really incredible piece of tech engineering.
It is, and our mission for this deep dive is to explore how this incredibly rigid, industrial-grade way of managing a device's operating system doesn't just survive that factory floor noise. It actually, well, it completely revolutionizes how you interface with artificial intelligence on a daily basis.
Yeah.
Right. It basically strips out all those hallucinations and the lag from your personal device.
Exactly. So to understand how this protocol fixes the AI experience for you, the user, we really need to start at the foundation.
Yeah, you have to look at why standard operating systems, like the ones currently running on your phone or your laptop, why they just fail when they get hit with a high-velocity flood of data.
Right. Because they do fail constantly.
They do. And the vulnerability really comes down to a baseline philosophy in computer science, one that's basically dominated software development for, what, the last 30 years?
At least, yeah.
Traditional operating systems operate on a philosophy of collect, detect, and
Correct.
they're inherently passive.
Passive in what way?
Well, when a stream of data arrives from a network, the system's first instinct is just to open the door wide. It lets all of that data into the main system RAM and then figures out what to do with it later.
Right, using that function we saw in the papers.
Yeah, a core programming function called dynamic memory allocation. It's often referred to as MALIC.
Okay, wait, let's unpack this for a second. When you say dynamic memory allocation, you mean the system just keeps grabbing more and more memory resources as the data piles up?
Basically, yes. It acts on the assumption that the environment is generally safe and that resources are virtually infinite.
Which they aren't.
Right. But the system collects everything coming in, expands its memory footprint to hold it all, and then eventually runs software scripts to scan through that giant pile of data to detect bugs or correct errors.
It's kind of like a hoarder who just keeps renting extra storage units every time they buy more stuff instead of, sorting through what they actually need.
That is a very apt comparison, honestly. And the fatal flaw is what happens when that system gets hit with something like 50,000 individual packets of data every single second.
Which is common in these high-velocity environments.
Very common. This passive collection strategy triggers what engineers call an interrupt storm. The processor has to literally stop its primary tasks 50,000 times a second to allocate a new block of memory and check the incoming data.
Oh, wow. So it's constantly interrupting itself.
Exactly. The system starts working so hard just to organize the chaos that it overheats. The memory becomes heavily fragmented, and eventually it hits an out-of-memory kernel panic and an AM, and the whole device just crashes.
So traditional OS memory is basically like a nightclub bouncer who just unhooks the velvet rope, lets absolutely everyone off the street inside, and then frantically runs around trying to kick people out after they've already started trashing the bar.
That's a great way to put it. It's a completely reactor posture, and computationally it is just exhausting for the processor.
Right.
But the SS-138 protocol we are looking at completely flips this paradigm. It changes it to detect, correct, collect.
Collect is the last step now.
Yes, it acts as a proactive, highly deterministic gateway. Instead of using dynamic memory allocation that just extends infinitely, SS-138 enforces a hard-locked 512 megabyte physical memory ceiling.
Wait, really? It caps the memory at 512 megabytes?
Hard cap.
In an era where apps routinely demand like gigabytes of RAM, it just never grows beyond that?
Never. That 512 megabyte footprint is carved out and allocated entirely at boot time, right when the device turns on.
Wow.
There is absolutely no dynamic scaling, no system bloat. The malloc function is structurally prohibited.
So it establishes an absolute physical boundary.
Right. If we go back to your bouncer analogy, this protocol is standing out at the street corner, mathematically verifying the VIP list before anyone even sets foot near the front door.
That makes so much sense. It detects anomalies and corrects them at the perimeter long before the data is ever officially collected into the main system RAM.
Precisely.
Okay, I see how capping the memory forces a kind of ruthless discipline on the software. But I'm trying to wrap my head around the physical reality of this.
Okay, sure.
If this gatekeeping is so aggressive and it's intercepting a flood of data outside the main memory, how does a regular mobile device actually run it without the CPU just melting down from the effort?
That is the big question.
Right, because the white papers explicitly point out that standard Android and Linux systems usually try to survive these data floods by bundling packets together.
They do. Standard operating systems use techniques to group hundreds of small packets into massive, single chunks before the CPU even looks at them.
To avoid that interrupt storm.
Exactly. It's a survival mechanism.
Hmm.
But SS-138 refuses to bundle. It processes all 50,000 packets every single second, individually and unbundled.
Which brings us to a really staggering metric from the spec sheet. It is doing all of this on a standard mobile chip, like an ARM Cortex-A53.
Yeah, standard consumer hardware.
We're talking about the exact same silicon inside a regular, budget-friendly phone you could buy at any electronics store.
Right, and the secret lies in the sheer microscale velocity of the math. Let's break down the timeline of what is actually happening inside that chip.
Okay, lay it out for me.
If you have 50,000 packets arriving per second, that means a brand new packet arrives at the device exactly every 20,000 nanoseconds.
20,000 nanoseconds. I mean, to a human, that's instantaneous. You can't even blink that fast.
Not even close. But what does that window feel like to a computer processor?
A lot longer.
An eternity. A standard Cortex-A53 processor completes a single clock cycle every 0.71 nanoseconds.
Oh, wow.
So the processor actually has a massive window of about 28,000 clock cycles available between each arriving packet.
That is a lot of downtime to work with.
It is. And the genius of the SS-138 architecture is that it completely bypasses the device's main RAM. It sets up an ultra-lightweight 48 kilobyte buffer right inside the CPU's ultra-fast L1 and L2 cache.
Oh, so it's operating right next to the processor's brain.
Exactly.
It doesn't have to waste time traveling back and forth across the motherboard to the main memory.
That physical proximity is absolutely crucial. And once the data is in that cache, it uses the chip's native hardware vectorization.
Vectorization? That sounds intense.
But without getting too bogged down in the acronyms, vectorization just means the hardware is capable of running parallel math problems across a wide register all at once.
Like doing 10 math problems at the same time instead of one by one.
Precisely. Instead of verifying the data piece by piece, it validates a whole chunk of it in a single processor heartbeat. Because it's doing this directly in the cache with parallel math, it fully processes that incoming packet in just 10 to 50 nanoseconds.
Wait, 50 nanoseconds out of the 20,000 nanosecond window it had available.
That's the brilliance of it. It finishes its highly aggressive gatekeeping job so quickly that it leaves the CPU completely idle for over 19,900 nanoseconds before the next packet even shows up.
Wow, and that resting period is how the device stays cool.
Exactly. The processor isn't working harder to filter the noise. It is just working infinitely smarter by leveraging structural efficiency.
I have to admit, I was pretty skeptical when I read that part of the source material. You usually need massive, power-hungry enterprise server racks to do this kind of real-time filtering without choking a network.
You usually do, yeah.
But you're saying this protocol forces a regular smartphone to mimic that hardware structure just by changing the math and putting a strict boundary on the memory.
The documentation proves it. Strict structural design and deterministic, highly optimized mathematics will consistently outpace raw, bloated computing power.
It's doing more with less.
Exactly. By stripping away the heavy, reactive software layers we've gotten used to, it turns a low-cost handset into an elite, industrial-grade data engine.
All right, so we know the bouncer is incredibly fast, and we know he lives in the cache to stay close to the action.
Right.
But the factory floor is still physically noisy. What if a spark of electricity scrambles the data in the air before it even reaches the device?
Which happens a lot.
Right. So if the data arriving is already corrupted, doesn't the system still have to halt everything to ask for a fresh copy?
That is the Achilles heel of standard networking. It relies entirely on binary logic, meaning everything is interpreted as either a 0 or a 1.
Basic computer logic.
Right. But when heavy electrical noise in the air flips a single bit from a 0 to a 1 in transit, the packet fails its basic mathematical verification when it arrives.
And because it's binary, the system has no idea how to fix it, so it just rejects the packet completely.
It rejects it, and it initiates an automated request back to the sender begging for a retransmission.
Ah, okay.
And if the environment is really noisy, these retransmission requests start piling up. The entire network bandwidth gets choked by systems constantly shouting at each other to resend corrupted data.
That sounds like a mess.
Engineers refer to this network collapse as a retransmission tax.
But the SS138 architecture gets around this, right? By ditching binary altogether and using a ternary erasure logic.
Yes.
It maps the incoming data into a multi-state structure. So instead of just zeros and ones, the protocol assigns 3 strict states to the incoming data.
Right, the ternary states.
So +1 means the data is valid, 0 means it is corrupted, and -1 acts as an explicit erasure flag.
And the introduction of that third state, the erasure flag, changes absolutely everything. The protocol no longer treats a corrupted packet as a hard binary failure that requires a retransmission.
It treats it as something else.
It treats it as a localized erasure channel problem. It instantly flags the bad data as a 0 or a -1 right there in the front-end cache.
You know, it reminds me of doing a crossword puzzle.
Oh, how so?
Well, if I accidentally spill coffee on the newspaper and obscure a letter, I don't pick up the phone, call the publisher, and demand they print and mail me a brand new puzzle.
Right, that would be the retransmission task.
Exactly. Instead, I just look at the surrounding letters, use the context of the word, and logically infer what the missing letter has to be.
And the SS138 protocol is doing something very similar.
The sources detail how it uses an algebraic ring logic to mathematically infer the missing corrupted data from the surrounding valid data. It's dynamically correcting the stream in midair without ever asking the sender to stop and resend.
That midair reconstruction is arguably its most powerful feature. Because the system never has to pause to ask for retransmissions, the data stream never stops moving forward.
No lag.
Zero lag. It creates a perfectly flat, predictable flow of information, completely free of the jitter that usually plagues noisy connections.
And this is where we have to pivot and connect this back to you, the listener, and your daily interaction with artificial intelligence.
Because this changes everything for AI.
It really does. We've been deep in the weeds of hardware specs and ternary math, but the primary mission of this deep dive is how this transforms the AI interface. How does managing memory at a nanosecond level actually stop an AI from hallucinating?
Think about the current experience of using a commercial AI tool online. You are interacting with massive dynamic transformers hosted on cloud servers. And anyone who has used them extensively has experienced hallucination creep.
Oh, absolutely. I mean, you start a long session, the AI is giving great answers, and then by the 20th prompt, it's suddenly giving you facts that directly contradict what it established 5 minutes ago.
Exactly.
Or it just drifts completely off topic into something bizarre.
That semantic drift is a byproduct of how standard models work. They are constantly accumulating tokens, the pieces of words they generate, and calculating statistical probabilities for what should come next on the fly.
So it's basically just guessing.
Highly educated guessing, yeah. But over a long session, tiny statistical variances in those probabilities begin to compound, and the model loses its structural anchor.
And how does SS138 fix that?
SS138 mitigates this at the hardware level by applying a 1-bit Boolean bit mask.
A bit mask. How does that anchor the AI?
Think of the bit mask as a rigid mathematical stencil. This stencil locks a highly strict 32,000 token vocabulary template directly into that ultra-fast CPU cache we were discussing earlier.
Oh, so it's right there next to the processor.
Right. And before the AI is allowed to commit a token to its output, that token is multiplied against this stencil using the nanosecond hardware vectorization.
That parallel math again.
Yes. If the token doesn't perfectly fit the strict structural guidelines of your original query, it is mathematically rejected before it even forms. The AI simply cannot drift from your parameters because the hardware won't allow the tokens to exist.
It forces absolute factual stability by cutting off the drift at the cellular level. That is wild.
It's incredibly effective.
And the specs point out an incredibly practical, everyday application for this voice-to-text dictation over a cellular network.
Oh, yeah, a perfect use case.
We've all been there. You're dictating a long thought to your AI assistant while walking or driving. The cellular connection drops a bar, and the standard interface just glitches out. It prints a completely wrong word or just drops the session entirely.
Because standard interfaces rely on that flawed binary logic. But a device running the SS138 architecture is constantly running that ternary signal repair.
The -1 erasure flags.
Exactly. If a piece of your audio packet drops out due to bad cell service, the system immediately marks it with a -1 erasure flag. The algebraic logic instantly reconstructs the missing audio data points based on the surrounding valid sound waves.
It mathematically fixes your speech in midair.
Yes, ensuring perfectly mapped input to the AI without a single stutter or dropped connection.
Okay, I do have to push back here, though, because I'm looking at the physical limitations of the hardware again.
Sure, go ahead.
If a highly optimized, modern AI model, even a smaller one, like a 4-bit quantized version of Llama 3, requires over 2 gigabytes of RAM just to hold the static model weights, how on earth can this AI interface possibly run under that strict 512 megabyte memory limit we talked about? The math literally doesn't fit into the space provided.
That is a crucial point of clarification, and it's something easily misunderstood in the architecture. The SS-138 protocol does not attempt to host the massive language model inside that 512 megabyte boundary.
Okay, so where does the heavy lifting of the AI actually happen?
The SS-138 layer sits on the local system bus, acting exclusively as an inline logic filter and token interceptor.
Like a toll booth.
Exactly. It is the ultimate mathematical middleman between the chaotic raw data of the outside world and the application layer where the AI lives.
Yeah.
Its sole purpose is to sanitize, mask, and correct the incoming data streams at 50,000 packets per second.
So it's just the filter.
Right. So the downstream AI, which might be streaming its massive weights from the device's disk or passing queries to a larger external system, only ever receives perfectly structured, mathematically verified tokens.
Ah, I see. So it's protecting the device from resource-heavy disk swapping. The AI never has to waste computing power trying to decipher bad audio or corrupted text because the SS-138 layer is doing all the dirty work in the cache before the heavy lifting even begins.
It maximizes the efficiency of the primary processor. It guarantees that no garbage data ever makes it into the core processing queue. And that garbage is usually what causes an AI to hallucinate or freeze.
Okay, so we know how it keeps the pristine data flowing smoothly, but what exactly happens to the bad data? Or what happens to the AI hallucinations that actually try to break through that rigid stencil?
This brings us to a really fascinating part of the spec sheet.
Yeah, the 0.4900 Irarubra floor and the dual-rail forensic auditing.
Yes. To put this in context, most AI systems today use a process called Retrieval Augmented Generation, or RE, to pull in outside facts. They use a metric called cosine similarity to check if the data they are pulling is related to your prompt.
Right.
Standard commercial models usually set a fairly loose generic threshold, something like 0.70 or 0.80 for semantic matching.
Like the system asking, is this paragraph roughly about apples? Close enough, let it through. It's looking for general vibes.
Exactly. It's looking for a neighborhood of relevance. SS-138, however, drops that threshold down to a highly specific 0.4900 baseline. But it uses it in a completely different way.
How so?
It does not use it for loose semantic matching. It uses 0.49000 as a strict majority truth baseline.
Okay, what does that mean in practice?
Well, to understand why, you have to know that in high-dimensional vector space, completely unrelated or fabricated data naturally sits near a score of 0.0. By enforcing a hard mathematical floor at 0.490, the system demands an explicit, verified, positive signal to proceed.
And if the generated text breaches the structural guidelines and drops below that 0.4990 floor, what actually happens to that packet of data?
The system activates a hard-coded look-ahead exception bypass. It triggers an immediate write block on the data, revokes the AI token, and deliberately collapses the active runtime container to violently purge the volatile memory pool.
It just annihilates the data.
Completely.
And the specs note it executes this memory flush in exactly 0.12 milliseconds. That is structurally flushed out of existence faster than the screen on your phone can even refresh.
It neutralizes unverified data at the absolute perimeter. The bad data is flushed before it can ever touch the CPU's floating point unit, and long before it has the physical time to render as a hallucination on your screen.
But what if it's borderline? Like, what if the cellular noise is heavy and the similarity score lands in this weird middle ground between 0.4900 and 0.5500? It passes the absolute floor, but it's dangerously close.
That edge case margin is where the dual-rail processing pipeline activates.
The 2 tracks.
Right. The architecture literally splits the processing path into 2 simultaneous tracks. Engine A keeps processing the normalized data stream in real time, so the system doesn't stall out and ruin your experience. But Engine B asynchronously intercepts that borderline edge case data.
So Engine B is acting like a background observer, watching the questionable data without slowing down the main conversation.
Engine B isolates a forensic mirror of that borderline signal. It compiles it on the fly into a 64-character SHA-256 cryptographic signature. And then it writes that signature directly to an independent, tamper-evident, append-only local disk ledger.
All without expanding the active RAM or asking for more memory because of the strict 512 megabyte limit?
Zero active RAM expansion. It creates a permanent, auditable diagnostic trail of anomalies and edge cases right at the perimeter, completely independent of the primary execution loop that is running the AI.
So what does this all mean for you, the listener, when you pick up your phone? It means you get total, uncompromising trust in your AI's output.
That's the ultimate takeaway.
You are getting an underlying architecture that takes a complex mathematical similarity metric and weaponizes it into a deterministic automated circuit breaker for truth. You get an AI that is mathematically locked to your exact instructions, repairing cellular dropouts in midair and executing a lightning-fast memory flush on anything that even hints at a hallucination.
It represents a massive paradigm shift for the industry. For decades, the commercial standard has been scaling for capacity, just throwing more gigabytes of RAM, more massive cloud servers, and more passive software layers at every problem.
More bouncers, basically.
Right. But this architecture proves we are moving toward a new era of absolute structural determinism, where discipline replaces raw power.
By enforcing that hard-locked memory footprint, utilizing ternary math to erase the retransmission tax and setting a ruthless 0.4900 truth floor, a standard consumer device becomes an unbribable, hallucination-free AI gatekeeper.
Which leaves us with a rather profound implication to consider based on the logic of these source documents.
What's that?
Well, if we can now deploy microsecond scale, mathematically rigid truth filters directly onto the local ingestion cache of an off-the-shelf smartphone, what happens to the entire global industry of digital misinformation?
Oh, that is a staggering thought.
Think about the mechanics of it. If a personal device is architecturally hardwired to mathematically annihilate structurally unverified data in 0.12 milliseconds before it ever reaches the processor or the screen, do we even need cloud-level content moderation anymore? The device itself becomes the ultimate arbiter of structural truth.
If the bouncer at the street corner is mathematically flawless, the bar never gets trashed in the first place, and you don't need a massive security team inside. Thank you so much for joining us on this deep dive into the SS138 architecture. Keep questioning the structure of the technology you use every single day, and we'll see you next time.